Alrighty, well let's go ahead and get started on a couple more things. This is evaluating limits analytically part 2. In the last one, which was video 3, we talked about strategies for changing the form without changing the value. That language that I use, changing the form without changing the value, ought to be extremely familiar to you, okay? I intentionally use that language over and over and over and over and over again in order to drive home kind of what we were doing and why. Always having sort of, at least in part, these sorts of problems in mind, such that you had your toolkit sort of filled with all of these strategies, such that this might be, relatively easy when we get here. And I hope that it's proving to be. But we basically talked about factoring to cancel, which is basically when I have a rational function, or I'm taking the limit of a rational expression, the function of which would have a removable discontinuity or a hole, meaning that there is of course a removable discontinuity. There's a hole there, but the factors cancel, and therefore you can actually change the form and evaluate it, because you're not really worried about the function at that point. You're worried about the function as we approach that point. Now the second one was we had sort of a radical in the numerator. Of course the same would prove true if that expression were flipped over and it was a radical in the denominator. I would have to, of course, multiply by the conjugate over itself. So I guess that's sort of shorthand for conjugate over itself. Now the third strategy I want to discuss with you is, of course, how to deal with the simplification of complex fractions. Okay? Simplification of complex fractions. And if you go ahead and look over at the worksheet on the left-hand side, number 2 is the kind of problem that we're going to be dealing with. Okay? So number 2, I'll go ahead and blow this up a little bit. Number 2 is this problem. The limit as x approaches 5 of 2 over x plus 3 minus 1/4, all of that over x minus 5. Okay, now how do we simplify complex fractions? Now obviously you can't flip them over as it is, right? Because you know that when you're dealing with a complex fraction, if you just have one fraction over another, division is an implied. A fraction is an implied division problem, and therefore you can just flip the denominator, multiply through, done and done, right? Obviously I need to go ahead. My first instinct needs to be to try and evaluate this by plugging in. But we can see right off the bat that if I plug 5 into this denominator right here, this x, I'm going to get 2 over 8. Well, 2 over 8 is 1/4. 1/4 minus 1/4 is 0. In the denominator, I'm going to get 5 minus 5. So if indeed I try to evaluate this limit by simply plugging in to evaluate, I'm going to get the indeterminate form again, telling us that we're going to need to change the form. Now obviously factoring to cancel doesn't work. Multiplying by the conjugate over itself doesn't make any sense. This is obviously a complex fraction. We've dealt with complex fractions before. Perhaps we're not too comfortable doing it in terms of the limit, but who cares about this limit notation right here? Simplify this. Just ignore the limit notation for a few seconds. Simplify this into a usable form, and then come back and we'll try to deal with it. Now in dealing with complex fractions, we walk through the strategy of how best to deal with them. Now you can get a common denominator in this numerator, but why in the world would you want to, right? What you really need to do is you need to figure out the problem. Like, what makes this complex? What makes it complex is the fact that there's a denominator in the numerator, right? What makes it complex, what makes it a problem, is divided by x plus 3. Divided by x plus 3 is my problem that I need to undo. So how do I undo divided by x plus 3? Well, I just multiply by x plus 3. That seems rather straightforward, right? Okay, well how do I undo divided by 4? And I don't have to, but might as well go ahead and clean up the whole thing. Divided by 4, the problem is solved by multiplying by 4. And therefore, if I go ahead and do this, I know that when I take this quantity right here, I have to distribute it to both terms. When I distribute it to this first term, the x plus 3's cancel, the 2 and the 4 combine to make 8. If I distribute it to the second term, the 4's cancel, and I just have to deal with x plus 3. Okay. Well, I know that I still have x minus 5 in the denominator, I still have x plus 3, and I still have 4. Now, some of you are about to make the rookie mistake, and you're thinking in your head, well, why don't I just go ahead and cancel out those x plus 3's? At which point you would send me into an absolute fit of rage, and I'd probably scream at you, so don't do that. Because that's really not an x plus 3. What that really is 5 minus x, right? Because once I distribute that negative, I get 8 minus x minus 3. So that right there simplifies into 5 minus x. Well, that I can cancel, because while it's not x minus 5, it is x minus 5's negative, okay? So I wind up being able to cancel that, and all I'm left with is a negative 1 in the numerator. I get negative 1 times 4 times x plus 3, and now I have simplified the complex fraction. It is now in a usable form. I can now plug in to evaluate. I go ahead and plug in the 5, and I get 5 plus 3, 8 times 4 is 32. I get negative 1 over 32, and that is the limit of that function as x goes to 5. Okay? So, we've done an example of factoring to cancel. We've done an example of multiplying by the conjugate over itself. We've done an example of simplifying of complex fractions. Well, let's go ahead and run through a couple of other ones that might actually be useful. I want to focus right here now on number 20. I don't really have a cute little name for that, so we'll just go ahead and leave it nameless. We have the limit as x approaches 1 of 1 over x minus 1 minus 2 over x squared minus 1. Okay? Well, what you're going to learn is that 0 over 0 is not the only indeterminate form. Okay? And what you get here when you try to evaluate each one of these rational expressions independently is you get a potentially sorry, it's late at night here. You get a potentially enigmatic situation here, because when you plug in here, you get 1 over 0. That's obviously going to be an asymptotic discontinuity for that expression right there. You're obviously going to also get an asymptotic relationship right here when you plug in 1. The question is, what happens to the whole expression? Well, I mean, I guess you could call this combining rational expressions, but basically you get an infinity, or it does not exist, minus an infinity, when what we really should do is, of course, just combine the rational expressions to see what becomes of it. Now, in order to combine them, I need to get a common denominator. Now, what factor occurs here in this denominator that is not in this denominator? Well, the answer, of course, is x plus 1. So if I want to change the form of this, I need to do that, right? I need to multiply that first rational expression by x plus 1 over x plus 1, and I'm going to get x plus 1 minus 2, okay? So let's go ahead, and that's x minus 1, and then x plus 1, x minus 1 as the factors of that denominator. Boom, boom. This should be 1/2. Okay? And of course you can check that graphically. Unfortunately, I don't have myself a cute little TI-84 anymore, but let's go ahead and see whether Grapher will help us. Okay, so that was going to be 1 divided by x minus 1 minus 2 divided by x squared. X squared. minus 1. And let's go ahead and let's graph that. Okay? Now that is the graph of my, that is the graph of the limit that I'm evaluating right here. And if you notice right here, right at the point where it's 1, if you zoomed in far enough, I'm sure there would be a hole right there. But right there, okay, is indeed the limit. The limit is right here, even though the function doesn't actually exist right here according to the original form of the function. I know that the limit does exist, and as x approaches, and let's zoom out so we actually get the integers right there, you can actually see the fact that at 1, this function has an output, or would have an output if there were no discontinuity, at 1/2, and therefore graphically we have confirmed that we have indeed evaluated the limit correctly. Okay? Now, a lot of this becomes much more difficult when I start combining stuff. Okay? And let's see whether I can actually, can I find one? Oh no, well I tell you what, I'll go ahead and see if I can find one of those really nasty ones for you. Or maybe I can just write one off the top of my head. But I'll go ahead and end this particular video. We're coming up on about 12 minutes right here. I think the last one was about 16. So I'll go ahead and cancel this. I'll come back with a few more examples of all the ones that I've done thus far and see if I can get into a few more of the more robust ones to sort of round out our review of evaluating limits analytically. But I hope that's been helpful, guys. Thanks for the increase in the output and the sort of output, feedback, input, whatever you want to call it, according to people signing up on the Twitter feed and of course emailing me information that I've requested. I hope these are helpful, guys. If they're not, or if they can be more helpful, I need feedback from you guys. But I hope y'all are doing well. I miss you guys. I'll talk to you soon.